Non, il a dit non. Ah, là, j'ai vu live. Ah, oui, mais
Je crois que nous sommes live.
Yeah.
Parce que je vous...
So it's good.
Okay.
Okay.
So I can start. So good afternoon, and thank you for being.
So I'm sorry.
Ah no.
I'm supposed to.
Sorry.
It's very formal in France. Sorry. So good afternoon, everyone. We are here to listen to the PhD defense of Mrs. Linda Lombardo. So Linda prepared her thesis here in Paris, in the GP department of Paris-Meudon Observatory, depending of University Paris Sciences Lab, under the supervision of Pierre Carlo Bonifacio and Patrick François. The title of her thesis is Getting Inside the Galaxy Story through Stellar Spectroscopy. The manuscript has been read and evaluated by two referees who gave their agreement for the defense. So these are, where is she? Marcella Marconi, who is researcher in Capodimonte Observatorio in Naples, and Sophie Van Eck, who is a researcher at the University Libre of Brussels. The other members of the jury, examiner, sorry, are Dr. Norbert Kriskib from Heidelberg University, Dr. Céline Reillet from UTINAM at Besançon Observatory. And then the invited members of the jury, Alessandro Mucciarelli from University of Bologna, and the supervisors. And I am Yveline Le Breton from Paris Observatory. So Linda, I will give now the lead to you. You have about 45 to 50 minutes to present us your work. I will make a sign 5 minutes before.
Okay.
And after that, the jury will ask some questions, and then we will deliberate and announce the decision.
Okay.
Thank you.
Thank you. Okay, so good afternoon, and thank you for being here today. So I'm going to defend my PhD thesis. And before starting with explaining you the different projects I've been working on, I would like to give you a general introduction. So my thesis work is part of what is called galactic archaeology. Galactic archaeology is the field of astrophysics that is devoted to the study of galaxies by studying the properties of their stellar populations. And why are we interested in stars? Because the stars are the fossil records of the gas out of which they formed. And so by studying the properties of stars at different epochs, we can study the different epochs of the universe. So for this reason, we are talking about fossils. It would be more appropriate to talk about galactic paleontology rather than archaeology. However, how we can date these fossils? Well, we know that each generation of stars, as they exploded as supernovae, they polluted the universe with metals. And by looking at the metallicity of the stars, so their chemical composition, we can reconstruct the history of the universe. So we can use the metallicity as a proxy of the age. And in particular, if we look for the most metal-poor stars, we can study, well, I don't know what is happening to my, sorry. I would love to, I don't know what is happening, sorry, okay. By looking at the most metal-poor stars, we can study the early stages of the universe. Another important property of the stars is their kinematics. In fact, stars have the memory of their origin imprinted in their orbits. For example, if we think about a dwarf galaxy that is having a merger with the Milky Way, we know that the merged galaxy is going to be destroyed by tidal forces, but their stars maintain the memory of their initial condition. And we can see this, for example, in stellar streams. An important instrument that has been fundamental in the past years in order to derive the kinematics of the stars is the Gaia mission, because it has allowed us to obtain precise measurements of distances and proper motions for more than 1 billion stars in the Milky Way. But the fact that we know how the star moves, the stars have memory of their origin from their proper motions. But we know that if two stars have similar orbits, it doesn't mean that they necessarily have the same origin. So in order to determine if two stars have the same origin, we need to look at their chemistry with the spectroscopy. And this is what has been done in the past years. So combining the Gaia parallaxes and proper motions with the spectroscopy from large spectroscopic surveys, we were able to discover complex substructures in the galactic stellar distribution that were associated to past accretion events. Probably the most important is the Gaia Soutenance that has been discovered thanks to Gaia. So we now know that the Milky Way is a complex and dynamic system that has accreted mass through mergers with smaller galaxies. So by combining the chemical information from spectroscopy with the kinematic from Gaia, we can investigate the formation history of the galaxy, the chemical evolution of the populations in the Milky Way, but also increasing our understanding of the physical mechanism and production sites for elements. So in this thesis project, I will going to show you some studies that are focused on the investigation of the chemical properties of different stellar populations in the Milky Way using high-resolution spectroscopy. The first two projects are kind of complementary, and they are both focused on analyzing and determining the chemical abundances in a sample of very massive stars in order to study the chemical evolution of the galaxy and also to study the physical mechanism for the production of neutron capture elements. The last two projects are focused on searching metal-poor stars in the Milky Way using two different approaches. The first one is focused on finding metal-poor stars using their proper motions, and so by finding stars with high speed. The second one is the pristine survey that is focused on finding metal-poor stars using the pristine photometry. The first project I'm going to talk about is the Mincher survey. The Mincher survey has the aim of determining the chemical abundances of a larger sample of metal-poor stars with metallicities between -2.5 and -1.5 in order to study the chemical evolution of the galaxy, but also to better understand the physical mechanism for the production of neutron capture elements. And in particular, this intermediate metallicity range is important because it allows us to distinguish between different formation scenarios for neutron capture elements. For the first observational runs of the Mincher project, for the target selection, we adopted the Stromgen photometry from the Townsend catalog and the Casagrande metallicity calibration for giants. In this way, we select a sample of metal-poor stars with metal-poor photometric estimate, and we observe these stars with different facilities. But when we analyze the spectra, we immediately realized that these stars were not old or metal-poor, but in fact, they were almost solar metallicity and rapidly rotating, so therefore young and massive. This problem, we tried to find why our target selection has gone wrong, and we, as we can see from the figure on the right, This is, in this histogram, you have the distribution of estimated metallicity from the Casagrande calibration. And you can see that according to the Casagrande calibration, these stars appear metal-poor. But if we look at the color magnitude, the Stromgren color magnitude diagram, we can clearly see where is the problem. We see that the stars are in a region of the color magnitude diagram that is in which lies both metal-poor old isochrones and young solar metallicity isochrones. So essentially what we think it might happen is that is a problem of age metallicity degeneracy. So we obtain a sample of 26 evolved stars that were of A to B type when they were in the main sequence. They have solar metallicity and they have high rotational velocities. From the evolutionary tracks, we deduce that these stars may have ages between 0.1 and 1 gigayear and masses between 2.5 and 6 solar masses. We decided to study these stars anyway, even if they were not in the Minche metallicity range, because these stars are interesting and poorly studied, due to the fact that the time spent by stars in this phase is short compared to, for example, the main sequence or the red giant branch. And also, we can obtain information on the stellar, on the evolution of stellar rotation in post-main sequence stars, as well as information on stellar mixing due to rotation. I measured the rotational velocities for the stars by performing a chi-square minimization fit on the observed line profile using synthetic spectra with different rotational velocities. In this way, I derived that the stars have VSNI between 4 and 27 kilometers per second. Since 2 stars in our sample were listed in a Washington double star catalog, we decided to look for other hints of a potential binary system in our sample. So we used the Gaia DR2 radial velocities, and we compared these values with the one derived by us. First, we see the stars that have a Gaia DR2 radial velocity errors above 1 kilometer per second, which is the typical error for stars at of this brightness. We also checked for stars that have Gaia DR2 radial velocities above 5 sigma from our, that differed by more than 5 sigma from our observed radial velocities. And we also checked for stars that were identified as probable binary stars from proper motion anomalies by Cervella 2019. What we found is that, in fact, 2 stars in our sample seems to have all the above mentioned characteristics. And so we suggested that these 2 stars may be likely binary stars. After the Gaia DR3 release, I checked if some of the stars in our sample were labeled as non-single stars in the Gaia DR3 variable catalog. And I found that 6 stars were in fact labeled as non-single stars with different properties. So we have an eclipsing binaries, 2 spectroscopic binaries, and 2 astrometric binaries. In this way, we have a fraction of binaries in our sample of 27%, which is compatible with the fraction of binaries of A-type main sequence stars found by other authors. From the chemical point of view, these stars, almost all the stars in the sample, show an underabundance in carbon and an overabundance in nitrogen, which combined with the C plus N plus O over iron abundance ratios, almost 0, seems to suggest that the material in the photosphere of these stars is mixed with the products of the CNO cycle. Another an important result and an interesting result that we obtained from the chemical analysis is that almost all the stars in the sample appear to be barium enhanced. And the interesting fact is that all the stars appear barium enhanced, but normal in the other S-process elements. So we tried to identify what is the reason of this barium enhancement. So we checked for the non-LT corrections for the barium lines provided by Corotin et al. 2015. And we found that this decreased the barium abundance by only 0.1 dex, which is insufficient to match the barium abundance with the other S-process elements abundances. We also check if we may have underestimated the microturbulent velocity in our stars, because we found that for one star, an increase in the macroturbulence of 0.6 kilometer per second decreases the barium abundance by 0.6 dex. But we have no observation that supports such high microturbulence. And also, of course, if we change the microturbulence of the star, this would affect also the other elements and not only the barium. We also check if, for example, a physical phenomenon could be responsible for this barium enhancement. So we checked if, for example, the magnetic field of a star could broaden the barium 2 lines due to the Zeeman effect. And so we check in the magnetic giant star Ekaparidani, which has stellar parameters similar to the one in our to the stars in our sample, but a very strong magnetic field, if the barium balance was enhanced. But in fact, what we found is that the barium over iron abundance ratio in this star is almost -1, which means that the star is underabundant in barium. Another possibility could be that our stars may be mild barium stars. Barium stars are a kind of giant stars that are enhanced in barium and other S-process elements due to the mass transfer with an AGB companion, which is now a white dwarf. So we compared our values for the S over iron abundance ratios with the one found for barium stars by De Castro et al. 2016. And what we found that according to De Castro et al., the limit to distinguish between a normal and a barium star is 0.25 dex. And in our sample, only 3 stars have have an abundance of S over iron abundance ratios above 0.25. So what we conclude is that maybe these 3 stars are compatible with mild barium stars, and they may be mild barium stars. But for the majority of our stars in our sample, this high barium enhancement is still puzzling and unexplained. We also compare our results with the one predicted by models with stellar rotation, stellar models with rotation. And what we found is that the Vcni that we derived for our stars are compatible with the models with rotational velocities with the rotational velocities predicted by models with omega between 0.3 and 0.6, where omega is the ratio between the initial angular velocity and the critical angular velocity. We also found that the nitrogen over carbon abundance ratios in our stars are compatible with the values predicted by models for clump stars. Even, as you can see from the figure on the right, our stars appear to be warmer than the maximum extent of the clump predicted by models. So I'm going now to talk about the first real sample of meteor stars that we were able to obtain after the first, after we changed the target selection. And in fact, now we have changed this target selection by using the star host code and using the kinematics of the stars. So by selecting stars with total velocity above 200 kilometers per second. We obtained from this new target selection a sample of 46 giant stars, and this time all the metaphor. And in the figure, you can have an idea of the quality of the spectrum we are using for this project. We were able to derive the chemical abundances for these stars for elements between carbon and zinc. We also studied the kinematics and we made some comparison with the chemical evolution models. What we found is that the new target selection was very successful in finding metal-poor stars with metallicity below -1. From the study of the kinematics, we found that some stars in our sample were compatible with the Gaia-associated Enceladus candidates and Sequoia candidates. And we didn't find any specific trend or offset between the chemical abundances of the stars that were candidates GSE or Sequoia compared to the halo stars. The second project I'm going to talk about is the CHERES survey. The CHERES survey has the aim to provide a homogeneous analysis of a sample of giant halo metal poor stars to increase our knowledge of the physical condition and formation sites of neutron capture elements. In the figure, you can see the very high quality of the spectra we are using for this project. And we are using spectra obtained with US at high resolution and high signal to noise ratio. For the first paper of this project, we determined the stellar parameters and chemical abundances of the stars for elements between sodium and zirconium. And this time, the metallicity range is lower than the one presented in the Minchu project. So now the stars have a metallicities between -3.5 and -2. The stellar parameters were derived from the Gaia EDR3 photometry and parallaxes using the iterative procedure described in the diagram. This iterative procedure is based on a grid of synthetic Gaia colors and extinction coefficients computed using Atlas 9 models. So what we do in this, this iterative procedure does is essentially to use the values of the photometry from Gaia, so the BP minus RP, the parallaxes, and the metallicity of the star to derive the stellar parameters. So the first thing is to derive the temperature by interpolating in the grid using the BP minus RP. Then the bolometric correction is derived through by interpolating in the temperature. And then the surface gravities were derived using this formula, which is essentially the Stefan Boltzmann law, using both the temperature, the bolometric correction, and the parallax. And then the procedure computes the extinction coefficients and derived the Redden colors. So the Redden G and BP minus RP. And once this has been done, the procedure starts starts another loop using the new values of BP minus RP. What is important in this procedure is that we are assuming a fixed metallicity. So once we have a first set of stellar parameters, we use this set to derive the metallicities. And then with the new metallicities, we compute again the stellar parameters. And in this way, we can reach a convergence after 2 iterations. Another important fact is that in all this procedure, we are assuming a stellar mass of 0. Solar masses. 0.8, sorry. So we derive the chemical abundances for the stars for elements between sodium and zirconium using MIGISFOS. Thanks to the very high quality of the spectra, we were able to detect hardly detectable ions such as silicon-2, scandium-1, and manganese-2. In general, our results were in good agreement with the one found in the literature, but we found that the chromium abundance was showing an offset between our derived value and the one in the literature. And in particular, you can see that this offset is present in both chromium-1 and chromium-2. We tried to guess what was the reason for this offset, and what we found is that essentially is due to the line selection that we used for deriving the chromium abundances. So as you can see, also our line selection appeared to be less sensitive also to the non-LT effects, because we can kind of almost reach the ionization balance. And this is clearly seen in this figure, in which I'm showing all the chromium abundances derived in different studies that we have done using the same line list. And you can see that now this offset is not present. Another important result that we obtained is that thanks to the homogeneity of the sample, we could detect 2 stars that are high in zinc. We think that this zinc overabundance could not be due to circumstellum component because we are using high excitation potential lines to derive the zinc abundance. Another interesting fact about these two stars is that one is R poor and the other is R rich, this according to the literature values. So it seems unlikely that in both stars, the neutron capture could have caused this zinc enhancement. We also tried to fit the abundance pattern of the stars by using supernova yields models using the StarFit code, but these models cannot reproduce correctly the zinc abundance in the stars, as you can see. And now, for this reason, we are collaborating with the Darmstadt Nuclear Physics Group to produce supernova yields models ad hoc for these two stars. Another interesting result is that we checked for eventual correlation between the different elements abundance ratios, and we found that the zinc over iron abundance ratios have a strong correlation with the nickel over iron abundance ratio. And in particular, as you can see from the figure, these correlations seem to split into different branches for values of nickel over iron above 0.05. A possible explanation for this splitting can be due to the different kinetic explosion energies of the supernovae as a given mass of the progenitor star. So what we think is essentially that the star with high zinc, so in the yellow, are formed in an environment polluted mostly by hypernovae, which are a kind of very energetic supernovae that seems to be able to produce larger amount of zinc with respect to classical supernovae. While the other stars, the one in the green, are probably formed in a gas polluted by classical supernovae. We also found that several stars in our sample seems to have a peculiar light and neutron capture elements patterns. And in particular, we found that this star has a strontium, yttrium, and zirconium overabundance with respect to the other stars in the sample and in the literature. We found one star with yttrium and zirconium overabundance with respect to strontium, two with the strontium overabundance with respect to yttrium and zirconium, and two with the zirconium overabundance with respect to strontium and yttrium. And once we will have a complete abundance pattern also for the heavier elements, we are probably going to try to develop models that can explain these peculiarities. In the context of the Ceres project, we observed one star that was kinematically associated with omega Sen, the omega Sen globular cluster. So we decided to derive the chemical abundances for this star in order to confirm or reject the possibility that this star could be associated with omega Sen. What we found is that essentially this star seems to be Cn rich and nitrogen and sodium enhanced, which makes it compatible with the second generation star of omega Sen globular cluster. So we think that due to this peculiarities, this star could be a second generation omega Sen star that escaped from the cluster. The third project is about the high-speed stars. So this is essentially the first true technique that was used in the past to detect metal-poor stars, to look for metal-poor stars in the Milky Way. And following this idea, the Cafau et al. 2020 paper decided to select stars, halo stars with transfer velocities larger than 500 kilometers per second, using Gaia DR2 parallaxes and proper motions in order to find metal-poor stars. The chemical abundances for the stars were derived from force spectra, And what they obtain is essentially that all the stars appear to be in a quite narrow range of metallicities, with metallicities between -2.5 and -1, with no extremely metal-poor star. Also, what they found is that the stars are chemically homogeneous, and their chemistry is compatible with the one of Milky Way stars. One of the interesting results about this work is that the subgiant stars in the sample appear to be younger than expected at this metallicity range. Among the possible explanation for this, the fact that the stars appear younger could be that the first one could be that these stars may be young metal, may belong to a young metal pool population that form in situ and that has not been discovered yet. The second possibility could be that they could be intermediate age stars with extragalactic origin, or they could be old field blue straggler stars that are evolving to the red giant branch. In order to distinguish between these different scenarios, a possibility is to determine the lithium abundance in order to discriminate between them. Why the lithium? Because we know that metal-poor warm main sequence stars share with metallicities below -1.5 share the same lithium abundance, the so-called speed plateau at the abundance of lithium around 2.2 DAX, as you can see from the figure. And apparently, blue straggler stars show no detectable lithium. In this figure, you can see that these are 4 spectra of 4 stars. The last one show clearly the lithium doublet. You can clearly see the line for the lithium doublet, while the other 4 stars show no detectable lithium. So our idea was to reobserve these subgiant stars with, at high resolution with UVIS in order to measure the lithium abundance. The proposal that I was the PI, it was accepted and 2 stars were observed. Unfortunately, we could derive only upper limits for the lithium abundance in the stars, and both stars seem, and for the first star, we found an abundance of lithium over 2 DAX, and for the second, an upper limit of 1.8 DAX. Even if we didn't have a precise measurement of the lithium abundance, we can still say something about their nature. The first thing is that in both stars, the lithium abundance is lower than the speed plateau, which makes them compatible with blue straggler stars. The second thing is that if we compare one of the 2 spectra with one of a star or with similar stellar parameters and with a spectra with a similar resolution and signal to noise ratio, we see that in the second spectra, we can clearly see the lithium line, while in our spectra, we cannot detect it. And this again makes them compatible with the blue straggler stars. So in conclusion, we think that these 2 stars are likely blue straggler stars. Okay, so since we have since in the previous paper in CAFAO 2020, these stars has shown a very small metallicity range and it seems to be homogeneous. What we thought is to select again stars with a high speed velocity, with high speed, and to check at high resolution what if these stars have some peculiarities in their chemistry. So 2 stars were observed with the Subaru telescope, and from the investigation of these 2 stars, we obtained a detailed chemical analysis from carbon to europium, and we studied the kinematics of these stars. And what we obtained is that from the chemical point of view, these stars are totally compatible with the one in CAFAO 2020, but also to the values found for halo stars. What is interesting is about their kinematics, and in fact, these 2 stars are have both retrograde orbits, and one star has also a kinematics compatible with the Sequoia candidates. Since in the paper of Aguado et al. 2021, they found that Sequoia candidates have some differences in the europium abundances with respect to GSE and halo stars. We checked if our stars have europium and barium compatible with the values derived for Sequoia candidates by Aguado et al. And what we found is that, in fact, this star seems to have values compatible with the one found by Aguado et al. However, I want to underline the fact that from the point of view of the other elements, these stars show no clear peculiarity with respect to halo stars, only in these two elements. The last project is the Pristine survey. And the Pristine survey is a narrowband photometric survey at CFHT, which combines the one-field imager megacam with a narrowband filter centered on the metallicity-sensitive calcium H and K lines. As you can see from the figure, these two lines are very sensitive to the metallicity of the stars at different values of the stellar parameters. And by combining this pristine photometry with the broadband photometric survey, such as SDSS and Gaia, we can infer photometric metallicities down to values below -3 in metallicity. And this has been proved to be a very highly effective technique, as we can see from the excellent results obtained by the Pristine collaboration. So, this first project uses the Pristine photometry to detect metal-poor stars in order to understand the galactic chemical evolution of copper and zinc, and to look for potential peri-instability supernova descendants. A peri-instability supernova is a very energetic supernova with a progenitor that have very high mass, with masses around 150 and 200 solar masses, that is supposed to leave no remnant. And the fact is that this peri-stability supernovae, from theoretical models, are predicted to produce in the stars that are polluted by their remnants, by their metals, to have a peculiar pattern in some elements. And in particular, these stars seems to have low abundances of copper and zinc. So we selected giant stars with a G magnitude below 11 and with a photometric metallicity estimate from a Pristine photometry and the Gaia photometry of about -1.5. We observed the stars with SOPHIE at 193 centimeters at OHP, with the telescope at OHP, and with the Neo-Narval at TBL. One in visitor mode, and I was the observer, and the other one in service mode. So we obtained a sample of 36 giant stars, and for these stars, we derived the chemical abundances of elements between sodium and barium, and we also studied their chemical properties. So what we obtained, the main results from the point of view of the chemistry, is that the first result is that the Pristine photometry combined with the Gaia photometry and parallaxes has proved to be very effective in selecting metal-poor stars with metallicity around -2, with a success rate of 77% for the SOPHIE sample and 100% for the Neo-Narval sample. We also found in our sample 3 stars that have a chemical pattern compatible with one predicted by models for PSL descendants. And from the point of view of the kinematics, we found that some stars in the sample, around 20%, have disk orbits with around 8% on thin disk orbits. Some stars in our sample have a kinematics compatible with the GSC structure, and the remaining are compatible with the halo, or they may have extragalactic origin. So the second project that is based on the pristine survey is focused on deriving the chemical abundances of a sample of pristine metal poor stars with a metallicity estimate below -3.5. The purpose of this study is to understand what kind of stars populate this parameter space together with extremely metal poor stars. As you can see, all the stars in this sample appear to have a metallicity below -4. This is not how the real photometric estimate, metallicity estimate, is derived from the pristine plus SDSS. This is just a comparison with synthetic colors. And so we obtain a sample of 19 stars that were observed with espadons at CFHT. When we inspected the spectra, we immediately realized that these stars were not so metal poor, and some of them look also in look like binary systems. And in fact, what we found is that 8 out of 19 stars in our sample have a double peak in a cross-correlation function. So these stars are actually double-line spectroscopic binaries. Due to the fact that the majority of the stars in our sample were sp2 binaries, or they were rapidly rotating, or the signal-to-noise ratio was too low for a chemical analysis, we were able to determine the chemical abundances only for 7 out of 19 stars. And what we found is that only 2 stars in the sample have a metallicity below -3, and only 1 with a metallicity below -3.5. We also found that 14 out of 19 stars are listed in the Gaia DR3 variability catalog, and were also in other variability catalogs in the literature. And according to the general catalog of variable stars, in our sample, we have found the majority of these stars are of type eclipsing binary systems, and only 1 an error Lyra. The eclipsing binary systems in our sample are characterized by short orbital periods and high rotational velocities, due to the fact that the rotation and orbital periods are synchronized. In our sample, we also found the 2 stars that are classified as RS Canum Veraticorum, which are a kind of closed binaries in which the primary component is an F to K subgiant star, and the coolest, so the secondary component, is a G to M dwarf subgiant. And what is peculiar in these stars is that they are characterized by chromosphere activity of solar type, as you can see from the figure. So we can see an emission, lines in the calcium H and K lines, and also in the H alpha. We also studied the kinematics of this sample of star, and what we found is that almost all the eclipsing binaries were on thin disk orbits. And we also found that one star, one of the 2 most metal poor stars, has a kinematic compatible with the GSC structure. The fact is that this star has a metallicity of -3.1, which is below the metal poor limit of the metallicity distribution function of the GSC, according to Feuillet et al. 2020 and Naidoo et al. 2020. But the star is compatible with the MDF of Bonifacio et al. 2021. However, even if the orbits of the star is compatible with the one of the GSC structure, this does not guarantee that the star is a member of the GSC, due to the fact that we can find 20% of the contamination from halo stars. So these are the main conclusions of this paper. And what I want to underline is that the fact that these stars appear the metal poor due to the fact that their calcium lines were weaker and appear weaker due to the fast stellar rotation and the stellar activity. Another thing that I want to underline is that now we are using a parameter that was suggested by Fernandez Alvara 2021 in order to clean the sample from variable stars. And if we apply this parameter, which is essentially the relative photometric flux error, we obtain 85% of photometric variables. We remove 85% of photometric variables from our sample of stars. And this is an important result in the prospect of using the pristine photometry for to select candidates for the largest spectroscopic survey, such as WEAVE or FORMOST. And that's all. Thank you for your attention.
So thank you very much, Linda, for this presentation. So we will now give the switch to the questions by the referees. So Marcella.
Thank you, Linda. Congratulations for the huge effort.
Thanks.
I have a few questions, but mainly just suggestions or curiosities. Are you planning to investigate the effect of next Gaia data releases on your results? Did you compare Gaia DR2 with DR3, for example, in some cases to see if any differences in the infrared parameters can be found?
To be fair, to compare the Gaia, I'm sorry.
Two different Gaia data releases. So in the first part of your thesis, obviously you relied on Gaia DR2, whereas in the second part on Gaia EDR3 or DR3. So did you notice any impact in the change of the accuracy of Gaia results?
In fact, not really. From the point of view of the photometry, not really. And also on the parallaxes.
Maybe the errors are smaller in some cases.
To be fair, I had a sample of, in general, bright stars, so the parameters were constrained very well. What I found really interesting and important and fundamental was the variability catalog. Okay. That was really, really essential. Okay. Because, before with the Gaia DR2, wasn't so obvious to check if a star was variable, or in a binary system, we should check for the error on the radial velocity. Yeah, so for me, that's the most important improvement.
Okay, thank you. And concerning the two lithium depleted stars that are likely blue straggler stars, yes. Did you notice any kind of different behaviors in the color magnitude diagram from the photometric point of view? Because blue stragglers should be located above the turn-off region.
I show you because I have the color magnitude diagram for this. So the two stars are in fact this one and this one.
Mm-hmm. So they could be associated to a fainter turn-off and.
No, because the metallicity is pretty much constrained. So I think that no, these one are subgiant. They're kind of evolving. So I think that
because blue stragglers should be somewhat more massive than expected for the typical turn-off of a stellar population. So I was wondering why they lie on the normal subgiant range. But then
I'm not sure I got precisely, but
maybe you are just too, and you need more investigation, maybe to.
Yeah,
to
because
confirm.
This was just a preliminary study because I had the spectra and I wanted to check if the lithium was detectable. So yeah, I didn't. In fact, this is the only project in which I didn't have the opportunity to.
Yes.
To complete also the chemical analysis because in fact we have very good spectra, and we only focused on lithium. But yeah, in this moment I don't really know how
but
to.
But it's a very interesting results indeed.
Yeah, absolutely.
Thank you. Okay, it's enough for me.
Okay, so you can take more time.
I don't want to.
Okay, thank you, Marcella. Sophie, please.
Yes. So thank you, Linda, for the very interesting thesis and for
the enlightening presentation.
It was a pleasure to read your work and learn about what you have done. So I have several questions. And so first, on the second chapter, where you have these stars with this strong barium line.
Can I take my my thesis?
Sure, of course, of course.
Because I realize now that it's here.
Yeah, so you have those stars where apparently you found enhanced barium.
Mm-hmm.
And so you say, oh, they could be mild barium stars, but curiously, they don't have any other S-process overabundance.
Exactly.
And so you have been investigating whether this could be due to different effects that you detail very nicely in your thesis. I was wondering how many barium lines did you use to derive the barium abundance? Only the resonance line, and were all the lines compatible with such a anomalous barium abundance?
I think I used maybe 3 lines to determine this. And I checked also because there was a paper that I read that they thought that was due to the line, the barium line, this enhancement. They thought that was because they were using this line. In this moment, I don't remember which one, to be fair. And they said that probably because this is something that is not new. This is not the first time that this kind of stars has been found. And in fact, I checked if this could be due to the fact that I was using one line or another, but apparently no, it doesn't depend on the line.
Okay.
Or, I mean, it's not so obvious, in fact, to understand if it's only for this, but yeah.
Because indeed, as you say, the first barium lines catalogs had a lot of false positive, I would say, a lot of mild barium stars, which turned out not to be enriched in barium in the end. And this was due to some effects which were, I think, never clearly elucidated on the resonance barium line.
Yeah, I wrote that.
Used. Yeah,
I remember.
So I was
this.
wondering whether your detection of apparently enhanced barium was because you used that line, or because. But if you have the same abundance from different lines, then probably.
Yeah.
Okay. So this is. And sorry, I don't remember. What is the binarity? Did you check the binarity of those stars?
Yes. Yes.
So they have the normal binarity rate, right? These are the one with the 27%, or?
Yes, exactly. This is the same sample.
Okay. Because if there are barium stars, there should be all binaries.
Yeah.
So yeah, this points towards a kind of spurious effect on the barium line, together with the fact that no other elements are enhanced. Yeah. So this is very interesting indeed. Okay. Okay. Thank you. And then when I go to page 35 of the thesis, you have a very interesting discussion about the difference between the parameters, the difference between the parameters, the stellar parameters that you get from spectroscopic studies and photometric studies. And so, yeah, this is very interesting. And I was wondering, well, you say that the observed discrepancy is due to the different approaches for the parameter determination. Can you elaborate a bit on that? Do you have an idea of why different methods? And this is a kind of open question now, because this is a big problem. Why different approaches give so discrepant parameters?
Okay, so regarding this study, what I found is that the only, or maybe I have a slide so everyone can see what we are discussing about. Yes, I have it. Wait a second. Okay. Okay. So this is this discrepancy that we observe in our parameters with the one in the literature. And my point of view, for example, for the temperature, we see that in fact, the only sample that is very different is the one of Roederer. et al. And in this case, I really don't know why. We were like discussing with it also with other people. It's not completely clear why he obtained such lower values. Because other studies, they used, for example, spectroscopy. They are not so in disagreement with the one from photometry. So it's kind of weird from what it concerned the temperature. For the gravity, no, it's pretty clear, because in the gravity we are using two different approaches. One, the one from photometry, we are using the parallaxes, and we are using this the parallaxes and the photometry. While in the spectroscopy, we are imposing the ionization equilibrium. And if we have mesopoor stars, the ionization equilibrium, deriving the gravity from the ionization equilibrium, can bring to a lower surface gravity. This is something that is kind of known, and we know that these discrepancies exist. So in this sense, it depends only on the method that one is using. Of course, if we have enough lines, good lines that we could rely on, we can use both, and it's just a matter of the method. In some cases, for example, for the giant stars, in that case, the ionization equilibrium was impossible to obtain. So we were forced to use the parallaxes, the photometry.
Okay, thank you. So I go to the Matas Pinto paper. Yes. About one of the two star that you have been investigated. This is around page 50 in the thesis. And then you have the two stars, and the one starting with 622. It's mentioned, actually not in your thesis, but in the paper, it's mentioned that it could be an AGB star. Is that correct?
Which one of the two?
The Tycho 622. Yeah, I think that one.
Yes.
It's because I think it's quite high on the red giant branch, and that it is written in the paper. So that's page 17 of the paper, actually, that it's a good candidate to be an AGB star. And I was wondering, if it is an AGB star, can you think of some way to test this hypothesis further?
Okay, because they were, in this paper, to check if it's an AGB star.
Yeah, because I can't find it. Yeah, because so, it's written here. Yeah, just it's page 17 here. It's written.
Okay. Yes.
The AGB solution is also reasonable for its photometry and parallax, and we are now more in favor of this latter possibility due to its low carbon and high nitrogen abundance. And this I didn't fully understand because, well, if it's an AGB, I guess the carbon should be enhanced unless there is HBB, but it's a kind of low mass star. So I was wondering, okay, do you think this AGB hypothesis is something we should investigate further?
Yeah, absolutely. And in this moment, I have no clear ideas on how we can do that.
I think it should be really investigated, because if it's indeed an AGB, which honestly I must say I doubt, but if it is an AGB, it would be extremely interesting. Yeah. So probably you could go to some spectroscopic diagnostics, and I don't remember the temperature of the stars, but resulting especially to some unstable elements might be the way to test that. Okay. And
so the temperature is 4,200.
Okay.
And the gravity is 0.7.
Okay. So maybe niobium could be used then. because niobium is enhanced, is not enhanced, well,
in AGB.
in AGB stars, and yeah, contrarily to what happens in extreme binary stars, because niobium comes from zirconium-93 decay. So niobium could be the way actually to test the AGB
Within
hypothesis.
nitrogen.
Yeah.
But I think
Okay, and then just maybe a last question, if I can. Okay. Yeah, maybe a general question. Now that you have all this expertise, given some, of course, observational constraints that you have, because okay, you have access to some photometric data, we have access to the Gaia data, of course. You have made a very interesting investigation of how to detect most efficiently the metal protons, and some of the attempts were very interesting because, okay, you had a large false positive start, but then you discovered many SB2s, so that is interesting in itself, of course. Absolutely. And so now that you have done this thesis, what would be the ideal procedure, most effective procedure to really target those low metallicity stars with minimizing the false positive ones?
Well, this is a very hard question to answer, because what we have found from the pristine photometry is that the pristine with the Gaia photometry, they work really well down to -3. For example, when we were selecting the targets for the copper and zinc paper, the pristine 19, we have like 100% in the neonormal. In the other one, no, because it was I was observing, and sometimes it was difficult to look at exactly the stars because I was limited in RA. But yeah, I think that going below -3, also with the pristine, is kind of hard. We can try. We are still trying to do that. And in particular, we are selecting targets for the pristine collaboration are selecting targets also for weave, because in this way we can, the idea, to be fair, it's very difficult to select the really metal poor targets. So, for example, when I was observing and trying to find -2 stars, metallicity -2, I was also checking for the radial velocities, because in general also metal poor stars are characterized by high speed. And so probably combining different hints from not only from photometry, but also applying some other cuts with, for example, the kinematics could be an idea. Yeah, but I mean, now we know that metal poor stars can be almost everywhere, also in the disk. So it's really difficult to detect them.
Okay, thank you.
Sorry. Yeah, I have first a somewhat more general question about this Minche project.
Mm-hmm.
So what is the scientific motivation to use this intermediate metallicity range? Wouldn't it be actually more interesting to go to lower metallicity, where you see the fingerprints of individual enrichment events, so that you can study the abundance patterns of these stars and compare them with nucleosynthesis models, rather than relying on galactic chemical evolution models to predict what is going on in this intermediate metallicity range?
I'm not sure if I heard the entire question, because there was some noise in the background.
Yeah, so basically the question boils down to why are you using the intermediate metallicity range and not the lower metallicity range?
Okay. Because essentially, I think I have a slide to clearly show what I'm saying. Essentially, this intermediate metallicity range is not covered in the literature. we have very few points in this range. So the focus of the project was entirely on that because we don't have data in that range. There is respect to lower metallicities that we have a lot of data and etc. And for this range, apparently there is not so much. Okay.
But maybe we have more data because the range is more interesting.
But why not studying also what is between?
No, my point is that, as I said, and when you go to higher metallicity, and in the way you have shown in your plots, you have to rely on the modeling of galactic chemical evolution and rely on a statistical sample to compare your observations with the predictions of the galactic chemical evolution models. So there is more modeling involved and theoretical uncertainties, maybe, in studying the individual nucleosynthesis events that contribute to the abundances. Okay, so, and I have one follow-up question on the issue of the barium overabundances. Because Sophie said it's a little bit strange that you only have an overabundance in barium, but not in the other S-process elements. So have you considered doing a differential analysis with respect to the Bensby et al. Stars? Because that could potentially pin down whether there's a problem in deriving your barium abundances. So if you, for example, study pairs of stars which have similar stellar parameters, and you check whether you can reproduce the results of the Bensby et al. Study with your kind of analysis, that would give you a hint or can confirm whether you have determined your abundances, the barium abundances, correctly.
Okay. So using another sample and derive the barium, is that the...
Yeah, use some of the stars of the Bensby et al. Sample and compare pairs of stars which in your sample with another star of the Bensby et al. Sample which has a similar stellar parameter combination, and then see whether you can reproduce the results.
Okay. No, I didn't try this. Okay. But in fact, for example, when I derived the barium abundance for the Caparidani, I used the same procedure, exactly the same. I derived the parameters. I did everything like in my sample of stars. So I don't know if this.
Yeah, just a suggestion. Then moving on to this Ceres project, you found a couple of peculiar stars with kind of deviating strontium, yttrium, and zirconium abundances. Have you considered comparing these individual abundance patterns with the pattern of the Honda star, the HD 122563, which is the representative star for the light element primary process abundance pattern, or the weak R process? So it's kind of a template abundance pattern. So the question is, how does that compare to the abundances that you get for those stars?
I'm not sure so this is this.
This is one star that was, so we think that this star has been enriched by the light element primary process, or the weak R process, as some people call it. And so this is a template abundance pattern to which you can compare the abundance patterns of other stars like yours.
Okay.
And so you can see if you see some similarities or some deviations. And if you see deviations, that potentially gives you some insight in the variation of the physical parameters in the site of this process.
No, I didn't check. I didn't do this.
Okay. And yeah, one more question is related to the sample of young metal poor stars. You were saying you suspect that these were produced in situ in the galaxy, but what is behind this argument? Why would you suspect that young metal poor stars would form in situ rather than having been accreted?
Ah, okay. No, it was just an hypothesis because we cannot exclude any. They could be also, in my opinion, probably is the less probable. So, but it's still because the point is that when I was writing the proposal, it was asked me to explain the other possibility, all the possibilities that one could have, and so I also add this. But in fact, I think if there is a young metapool population that forms in situ, it will be very interesting, but we haven't found it yet. So I only add it because it is not completely, we cannot exclude it a priori among all the possibilities.
And can you remind me whether you have investigated the kinematics of these stars? So potentially you could... The kinematics of these stars.
No,
because if you have retrogrades,
not yet. I haven't done it yet. Yeah, only
So
the lithium abundance.
this would also give some hints towards what the reason might be or the nature of this population.
Okay, thanks.
And then I have a few somewhat technical questions. You were saying that you were using a genetic algorithm for the equivalent width fitting. And what's the motivation for using that rather than some other kind of fitting algorithm, like chi-square minimization or downhill simplex algorithms or something? So what's the advantage of that genetic algorithm?
Can I answer?
Yes.
It's more robust to local minima. So it's very efficient. So when you have local minima everywhere, it isn't forming that. So it's more robust at chi-square than anything else.
Oh, okay.
And it's very fast. Very fast.
Thank you. And then you have shown on page 37 of the thesis 2 diagrams of the chromium abundances over Fe on H. And so you used different species. And can you tell us which of these two diagrams you would trust more and why? So it's a chromium 1 over iron 1 and the chromium 2 over iron 2.
We can trust.
Which one of these diagrams would you trust more?
From the point of view of the abundance?
Yes.
Probably the chromium 2.
Okay.
Because it's less sensitive to the non-T corrections.
Yeah. Okay.
Yeah, and also, but in our case, it was quite good. Also, the ionization balance. We I don't know why we chose lines that were less sensitive. So yeah, but in general, we usually trust more the the ionized species because they are less sensitive.
Okay, and why is that?
It's because they are, for example, for iron, they are I don't know how to translate it. They are the majority of atoms in the atmosphere. Okay, I didn't know, and so for this reason.
And so what is the main non-LTE effect that we see here in the minority species of iron?
For iron, we see that the abundances are lower. The abundance of iron when there is the LTE is shifted. It's lowered in general compared to it depends in the sense, but usually for iron is lowered.
Yes, but what is the physical reason for that?
why
it is lower, or why do we see the non-LT effect, and especially in metal poor stars?
Because
Well, in metal poor stars, you have a lower opacity and therefore a stronger UV radiative field, and therefore over ionization.
yeah.
Okay, thank you.
Thank you.
Okay, thank you for this nice presentation. So I had many questions, but some have been answered yet. So, maybe I will just start with a methodology question. For the series part, you are using you developed an iterative process using Gaia photometry, and as I understand, in the first part, the means part, you compared with the synthetic, you fitted synthetic spectra to get the parameters. So why did you use this method in the Ceres survey? Is it because it is done to be applied to many stars? Is it faster or?
Well, in general, yes. It's the method that we use when we are using photometry, and this is pretty much fast. And in fact, in this case, we have large sample, and yeah, it can reach the results in a very fast way.
Okay. So if I stay on this part, the surface part, it's about what you were talking about, Norbert, but it seems to me, so you said that in this plot, page 37 that you showed also here, you don't see a trend that has been seen with other sample, but I was wondering if you just remove the two stars, the two lowest metallicity stars, it seems to me that the trend seems to be also in your sample. And so I was wondering if it could be something special with these two stars, which have low metallicity, but higher chrome over iron abundances. It's
I'm a bit
the
lost.
plot figure 3.4, page 37.
In the chromium.
Yes.
Okay. So we are talking about the stars with the chromium.
Yes. You said that compared to other samples, so the
yes. Okay.
Kerel and Ishigaki sample, it seems that there is a trend in the sample, a slope, that you said that you don't see it in your sample, but to me, if you remove the the two low metallicity stars, we can guess
exactly.
that there is also a trend. So I was wondering if something special could happen with these two stars, or
No, I agree. No, exactly. I think it's just the fact that these stars are like this, but yeah, in fact, it's difficult to say there is no trend because we only have, I think, 4 stars. Yeah. But no, there is nothing really special about them. They're just, they have this chromium abundance, and that's all.
And physically, could they be, special compared to the other sample?
No, I think it's just due to the line selection, how we derive the chromium abundance essentially. But no, I don't think they are special.
On the high speed stars.
Yes.
So you said that most probably your stars are blue struggles stars. But then in your manuscript, you also said that there are stars with a lithium dip, in particular in open clusters. And so that was an open question in your manuscript. And then in that case, would that mean that the stars, if they are with a lithium deep. Does that mean that they originate from an open cluster, or they have been ejected recently from an open cluster?
Well, in fact, the point why the main point on why we exclude this hypothesis is because there is we have never found a metal poor star with in the lithium deep.
Mhm.
So I think it was just a way to say that, yeah, there is this possibility, but we think it's not likely. And yeah, no, I don't think it could be the case.
Okay. And then for the next part, so you are also talking about the two spatial stars, and in particular because they have isotopic carbon ratio of about 4.9. But I was wondering if it's not something expected for metal poor stars, such isotopic ratio, or could it be that they have on different evolutionary stage than other stars? And as you said, Sophie, could they be AGB stars? Because I think they have normal isotopic carbon ratio for AGB stars, low metallicity AGB stars. Or could they, I don't know, have a different mixing process than other stars? And last, do you think that asteroseismology could help deriving their evolutionary stage to know a bit more about these two stars? That's a lot of questions.
No. I'm a bit. To be fair, astroseismology. I'm not really. I don't know a lot about astroseismology, so I don't really know how to answer.
Yes.
To be fair.
So yeah, so the other parameters, delta nu, nu max, and there are papers that show that you can, with these parameters, you can say if it's a clump or AGB. I think I'm not specialist at all, but okay. And yes, and the other thing is, for me, this isotopic ratio was normal for low metallicity stars.
Yes, yeah. In fact, I think that there was the point that also the isotopic ratio confirmed that the stars are giants, essentially. Yeah, I think it's kind of normal. There is nothing weird.
And so maybe one last question on the means survey. So you showed some comparison with other samples, but you didn't tell much about what the comparison tells. So that was on the chemistry, page 23 maybe. Yes, so you made a comparison with other samples, but are they similar samples? Because you have some shift between the samples. Are there similar samples? And what can you tell from the comparison with the other samples?
I'm a bit lost. What are we talking about?
So in the means survey, the plot 2.5, page 25.
Yes.
So you have your sample and other sample, but are there different type of stars? Or
yeah, absolutely. Yes. The Roder sample is A-type main sequence stars that, according to Rayet, are normal A stars. And the yellow sample, I think they're like FG stars. I don't remember if they are main sequence. It's written in the paper. In this moment, I don't remember. And the point was that if we look at the carbon abundance, for example, we can see that the Rayet stars are underabundant. And the other sample, I don't remember. I think it's similar. So FG, also in that case.
Okay. And then you say that you have one peculiar star in your sample. with low, all but one star have low C over Fe and high N over Fe. And do you have an explanation why this star is different from others? Is it because the mixing process are different?
We are talking about the carbon and nitrogen.
Yes,
Okay.
yes.
I think that these two stars are not in the clump.
Okay.
That's the main
That's
difference.
another-
Yeah, and these two stars are the most metal rich in the sample, and also I think they are the less massive also. Yeah, I think these two were. Yeah, maybe they're not in the same evolutionary stage.
And I have a general question, a naive question, probably. So you are using, all your studies are about giants. And so in giants, you have, I guess, a complex mixing process that can change your abundances on the surface, depending on, I don't know, the rotation, thermal mixing or whatever.
Mm-hmm.
And how can you disentangle between this effect and the archaeology, the fact that the origin of the star?
Well, I think that it's yes. This is something that we kind of deal with, and the fact is that for studying the properties of old metapool stars, usually no. In fact, we can use also main sequence. I think is not something that is only linked to giants. Giants are only easier to analyze sometimes because they are cooler, and so when you have a very small lines, it's easier to detect metapool stars when they are giants. But yeah, in principle, there is no reason to choose one or another.
Yes, I was wondering if it was more complicated to conclude with giants rather than main sequence, because in giants you have other process that may have changed a lot your abundances on the surface.
It depends on what are you looking at, what kind of elements are you looking for. For example, I don't think it affects a lot, for example, the iron. So yeah, but of course it's a complication in this, but it's something that we kind of know because of the stellar evolution models. So it's something that is not so unpredictable in a certain sense.
Okay. And the very last question. So you said that Gaia GR3 was very good for the variability and binary parameters. And what about the abundances and the astrophysical parameters that have been also published in the last data release? Do you plan to compare them? Have you compared them with?
Yeah, I compared the metallicities, and I didn't find a strong agreement. To be fair, I think that is something that must be improved in that sense, because sometimes they're not very compatible with the values from high resolution spectroscopy.
Okay, thank you.
Okay, thank you, Linda, for your complete presentation. So I have a couple of questions, but there are not two questions. I wish to know your opinion about some points discussed in your works. First of all, concerning the stars discovered and escaped by Omega Centauri. Why so important, in your opinion, to search and to find this kind of stars? In other words, it's just a funny star, a curiosity, or this kind of escaped stars can be useful to understand something about globular cluster or halo formation?
Yeah, it could be important, I think, because for example, when we don't have some structures in the Milky Way, for example, when we are looking at stellar streams, now I'm thinking about that, and by looking at the chemistry of the streams, we can also distinguish between, for example, a globular cluster or a dwarf galaxy, because by looking at the chemistry. So yeah, I think it's important for this reason, because sometimes we don't have we have this kind of stars that escaped, and it's important to understand if they were belonging to another structure or something like this.
Okay, another point. In the next years, we will be available a number of new spectrograph working in near-infrared regime. I think to MOONS, CRIRES Plus, ANDIS at the ELT. Do you think that this kind of spectrograph will be useful for some of your field of research? Or in other words, if you have time with this near-infrared spectrograph, they will be useful for some of your research or not?
Yeah, absolutely. I think for sure.
How?
But in this moment, I'm not planning. I don't have any idea to use this spectrograph on my works. But yeah, absolutely, that would be very important. And
for instance, to measure some abundances, some.
This moment, I don't have any idea.
Is obviously there are new spectrograph and new field of research. So a last question, but is my curiosity. Can you show again the plot zinc versus nickel?
Yes, absolutely.
Because this is a fantastic plot, because you have in hand a diagnostic probably to separate, discriminate between hypernova and supernova. But just a curiosity, in the two groups that you show, the same nickel and different zinc. I understand the different zinc because zinc is produced mainly from hypernova. But if I well understand, there is an enrichment in nickel in these stars, or you consider all these stars with the same nickel? So in other words, the stars in green are enriched in nickel and not enriched in zinc. And in this way, the normal supernova produce zinc with respect to the other stars. I don't understand this point, because I understand the difference in zinc only.
As far as understood, the nickel abundance depends on the mass of the progenitor.
Mm-hmm.
And in classical supernovae, you have less production of zinc, which is kind of the same.
Okay.
As far as understood. And hypernovae, you have this large amount of zinc. So are this one that actually are outliers in a certain sense.
Okay, and just a final comment for your work searching for zinc-rich stars. Recall that also the zinc-poor stars are important because they are probably candidate to be accreted by external galaxy, because the contribution of hypernovae strongly decrease, and also the abundances of zinc decrease in Sagittarius, Magellanic Cloud. Zinc is underabundant with respect to the Milky Way. In this way, remember that if you find some zinc poor star, they are very important. Okay.
Okay. Thanks.
Okay. Thank you.
So thank you very much, Linda, for your talk. I would just have one question, and so your project became very difficult because we started with the idea that you were going to analyze stars spectra from WEAVE. We were expecting WEAVE spectra to arrive before you ended the project. And then this was not the case. Now, probably next month, we shall see the first data. So, if you were to do this project again with the foresight that the WEAVE data was not coming, and so you remove WEAVE from the equation, what would you do? What would you do differently from what we have done?
Well, I was thinking that maybe something that I should have used more was probably the pristine photometry, because I didn't use it a lot, to be fair, except from in the last period. So probably I would have used it more the data from pristine, and because I was blocked by the fact that most of the candidates were like frozen for the future follow up. So yeah, probably I would have used more pristine. That's a thing.
Yeah, thank you for nice and very dense talks. It's like, yeah. I have just one comment. The PI of Minch is Gabriele Cescuti. So you know he's doing models of chemical evolution. And so the main goal of Minch is to constrain models of galactic chemical evolution. On top of that, you get a lot of data and results, and then you can compare with what we find now with Gaia Osage and so on, all these star streams. So in itself, it's very important. Yeah. That's what I have to say.
Thanks.
We had a lot of discussion when she showed us this very high barium. You can imagine that we were not happy. So we try by all means to understand what was the source of these high barium abundances. So we had a lot of discussion at that time. So I don't have any question anymore.
Okay, thanks. So I'm fine.
Okay, I have very short questions about the model atmospheres, because everything in your work is based on, not everything, but a lot, is based on this, and your error bars on the abundances and so on. I guess the error bars you give are internal error bars related to your model atmosphere, which are Atlas 9 and 12, depends.
Yeah, it depends.
Yeah? So I have some questions. In the paper by Matas Pinto, Arroa, it is written that the solar mixture used in the model atmosphere is the Cafao et al. 2011. Mm-hmm. Is it the case for all the models you used, or do you use different model atmospheres with, I don't know, older solar mixtures in them?
I'm not sure. I didn't understand very well because we are quite far, but we are talking about the values.
The solar mixture.
Yes.
In the model atmospheres.
For the solar composition, we use the Cafao and Loders for almost all the papers in which I'm first author, but also in the others, I think. And for the model atmospheres, we use it depends. For Migisvos, it uses Atlas 12, but in the other cases, Atlas 9. And I don't know if.
Okay. I don't know, because sometimes old solar mixtures are used, and that may change a lot.
Yes, absolutely.
Solar metallicity is very different.
Exactly. Absolutely agree. And in fact, all the plots that I've shown, they were the abundances were scaled in order to be consistent. So I scaled everything is referred to Cafao or Loders solar abundances. Okay. So everything is compatible from that point of view.
Okay, so because I think it's not written in your manuscript. This.
Yes,
it's in the paper by Arroa Matas Pinto, but yeah.
Okay. Yes, absolutely. Yes, we scale everything in order to be consistent and in order not to have the differences that could be due in adopting different solar mixtures. Yes, absolutely.
Okay, thank you. So I also wonder about the plane parallel hypothesis in the model atmosphere, because you treat giants, which are huge with maybe spherical effects. Do you know how it could impact your result?
In this case, we use the LTE approximation with a plane parallel atmospheres. The point is that when you are assuming another configuration like spherical models, they're more sensitive to other effects like the non-LT. And so it's, in this case, in order to, I don't know how to say, but I don't know, I'm a bit...
Okay. Also, I noticed that in the paper on the Minch survey, you had to reject 5 stars, which are 10% of your sample, simply because their effective temperature is smaller than the limit of the Kourooks model atmospheres. So I wonder whether there are other model atmospheres, more modern, like Mark's model atmosphere, which go well below this temperature limit, and which are used in Gaia pipeline, in Plato. They will be used also in the Plato pipeline. So would it be difficult to change? Because they are available, those model, Mark's model atmosphere from Sweden, Uppsala.
Yes, but I'm a bit lost. What is the...
Well,
in general, you mean?
Yes,
or?
In general, because here you lose 10% of your sample. You have 46 stars, and 5 of them cannot be studied because they are too cold, if I understood correctly.
From the Minch?
Yeah.
Okay. Because I was a bit confused. I didn't understand.
Yes, from the Minch, yeah. Sorry if I was not clear.
So, to be fair,
my question is why going on with those Atlas model atmospheres? Is it because the pipelines are?
If you want to answer, Carlos.
Okay. Maybe the pipelines are already ready.
Yeah, essentially.
But you lose part of your sample. So I think it's a pity.
I cannot answer. No, I'm joking, but yeah.
I think I must answer that. Sorry. In the Minch sample, the limit was due to the fact that the Atlas 12 grid computed by Lucas Bordone arrives at 4,000 degrees. Atlas 12 is very difficult to converge below. We plan to have Alessio has computed an extensive Atlas grid that will be published soon, I hope, that goes down to 3,700, and we will show in that paper that there is no substantial difference between Mark's and Atlas models. So why do we continue to use Atlas models? Very simple reason. We control the code. We compute the model atmospheres as we want. We can change the physics as we want. Mark's is a black box. And in fact, we had a lot of difficulty in the Gaia ISO survey. I mean, me and Elisabetta, etc., in trying to use the Mark's grid, because it was decided to use, you had to use the Mark's grid, but it was full of holes. We had to interpolate a lot, and we could not do, we had to use turbospectrum, changing the microturbulence, because we did not have the correct microturbulence models, because Mark's group would not compute that, etc., etc. Instead, with Atlas, we can do all we want. So we have much more control. So that's the main reason.
I understand that Mark's is not perfect yet. So they plan to deliver for Plato preparation a public version, but I guess it's simplified.
And in addition, Mark's is limited to 8,000 degrees.
Yeah.
Mark's is not.
So maybe I have to ask because people in the audience with the PhD have some questions. No? If not, so we can move on to the deliberation.
Je sais pas, je crois que during the discussion, everything is going to be closed, the streaming. We are still on live, but I.